So, have you ever wondered why artificial sweeteners work and make your brain think that you're actually eating sugar by giving you the sensation or taste of sweetness? It has to do with the fact that um, the shape of the sweetener fits into the something called a receptor where sugar usually binds to. So, because of the shape, and they were engineered to be that shape, they kind of trick your brain into thinking that you have eaten something sweet. And it all has to do with the structure and the shape that it has. So structure is what determines properties. So along with the types of bonds you have in atoms, the arrangement of atoms, the shape is also very important to determining properties of a compound. So we learned so far, off of Lewis theory, we learned about different regions of electrons in an atom. They can either be bonding pairs or they can be lone pairs. We are going to talk about molecules in this part of the chapter as if they are geometric figures. And by geometric figures, we just mean 3D shapes. And these 3D shapes have angles relative to the central atom that we call bond angles. So what we base off of all of this about structures and shapes of compounds is we base it off of VSEPR theory. So VSEPR theory is valence shell electron pair repulsion theory. We shorten it to VSEPR again because chemists are lazy. And this is what helps us predict molecular structure. So this again includes those bond angles that we were talking about, and they're relative to that central atom. So the main idea about VSEPR, I'm going to keep it simple, is that electron groups are antisocial. So electron groups, whether they are lone pairs, single bonds, double bonds, triple bonds, or even single electrons, they repel one another. They don't like being next to each other. So these electron groups, no matter what they are, bonding groups or lone pairs, they do not like being near each other. They will repel each other. So the shape that the compound will take is the one in 3D space that will allow the most separation, so the most space between those electron groups. So that's the main idea about VSEPR. Electron groups want to be as far away from each other as possible. So we talked about the bonding groups again and lone pairs. But in the rest of this chapter, sorry, this is a very long chapter, we are going to categorize electron groups as any of the different types of groups we just talked about. So lone pairs or bonding pairs will be considered an electron group. So here we have NO2. NO2 in this case has a double bond to this oxygen, a single bond to this oxygen, and then we have a lone pair. We're going to count each thing around this nitrogen. So 1, that lone pair, 2, that double bond, and then 3, that single bond. We have a total of 3 electron groups. So you just count however many things you have around that central atom. This should say 1 lone pair. I don't know why it says 3, I'm sorry. But we have 1 lone pair, 1 single bond, 1 double bond. That's a total of 3 electron groups. So there are 5 basic arrangements of these electron groups around a central atom. It is all based off of a total of 6 bonding electron groups. So in this chapter, in this class, we're not going to learn about anything that has more than 6 bonding groups around it, bonding electron groups around it. These can exist on very large atoms, but it's really rare, so don't worry about them. So we just have 5 shapes, okay? And the maximum we're going to see is a total of 6 electron groups around a central atom. So the first of these 5 basic shapes is whenever we have 2 electron groups around our central atom, and we have something called a linear electron geometry. So whenever you have a linear electron geometry, the bond angle will be 180. Here we have 2 examples. We have carbon dioxide, which has a double bond, either way, that's 2 electron groups. Here's the Lewis structure, so you can see the comparison, and then here's the actual like ball and stick model. Sorry, I had to think about that one. And here you can see the bond angle between the two different bonds relative to that central atom. So they take the angle that will give them as much space as possible. So in this case, to give these bonding groups as much space as possible, they're going to be 180 degrees away from each other. And then here's another example. This time we have single bonds instead of those double bonds, but still it's a linear geometry. Next, we have trigonal planar electron geometry. This occurs whenever you have 3 electron groups. Whenever you have this geometry, your bond angle will be 120. Again, remember, this is to maximize the space possible between electron groups. And the way that this happens is that you see that the bond angle keeps decreasing. And it's because you have more electron groups, so there's less space to space these. There's less 3D space to space these groups out. So here's an example. We have boron trifluoride. We have single bonds, and the trigonal planar. So I'm going to explain what the names mean. Trigonal planar. Trigonal has to do with the fact that it's a triangle shape, right? Whenever we connect these like dots, right, we have a triangle. The planar has to do with the fact that it's in one plane. It's not 3D, it's just, it looks like a fidget spinner because that's the actual shape it is. So it's flat the same way that a fidget spinner is. So this is like the center of the fidget spinner, and these are the little circles outside, and it's flat in the same exact way. Next, we have tetrahedral electron geometry. This is whenever we have 4 electron groups around our central atom. The bond angle that your outer atoms will take around that central atom will be 109.5 degrees away from each other. So between these two bonds, we have 109.5 degrees. Now, where does this name come from? Tetrahedral. So tetra refers to the fact that we have 4 faces. So here you see the shape. This is the actual shape. And we have 1, 2, sorry, I'm butchering this, 3, and then at the bottom, 4 different faces. So hedron, hed, refers to faces, okay? Keep that in mind for when we start talking about octahedral. Next, we have our trigonal bipyramidal electron geometry, and this is whenever we have 5 electron groups. So I would say this is the most complicated one out of the 5 different electron geometries, and this has to do with the fact that we have 2 different types of positions. We have axial and equatorial. So equatorial positions refer to the positions going horizontal around the central atom, and again, equatorial, equator, same thing. And then axial refer to the vertical ones. So they're like at the top and then the bottom. So we have these 2 different types of positions, and we have different bond angles relative to these. So for between the equatorial positions themselves, we have 120 degrees between these. Between the axial and the equatorial, we have 90 degrees. And then between axial and axial, we have 180. Here's an example. We have phosphorus pentachloride, and then this is the ball and stick model. And then to explain what this shape, the name of the shape means, so trigonal refers to the face, right? So it's a triangle. And then the bipyramidal refers to the fact that we have 2 pyramids kind of stuck together on the top and then the bottom. I hope you guys can see that. We have a pyramid basically up here, right? I'm going to shade it in, and then I'll leave the other one not shaded. We have a pyramid up here, and then one kind of stuck under it the opposite way around under it. So that's what bi means 2, and then pyramidal, 2 pyramids. So triangle face with 2 pyramids stuck together. So that's where that name comes from. And then finally, we have octahedral electron geometry. This is whenever we have 6 electron groups, and the reason I was kind of harping on that tetrahedral and what hedral means, this has to do with faces. So octa has to do with faces, not the amount of electron groups. So whenever you have octahedral geometry, your bond angle is 90 degrees. All of your positions are equivalent. They're not like the trigonal bipyramidal where you have axial and equatorial. In this case, you have the exact same type of position no matter where you are. So this is how it actually looks. Again, 90 degrees between all of the angles. And then whenever you look at the shape, so imagine that you draped like a cloth over this or a sheet over this. How would the shape look? It looks like this. And you have, again, kind of pretty similar to the trigonal bipyramidal where you have like 2 pyramids kind of stuck together, one on top and then one on the bottom through the bases. But the name comes from the fact that we have 8 faces. So if you look at them, we have 1, 2, 3, and then 4. And then if you count the ones at the bottom, that's going to be a total of 8. So that's where that name comes from. So this is a nice little table that summarizes all the different electron geometries. You will also see it maybe called electron pair geometries, but I like to just say electron geometry because it's easier. Here we have the number of regions, so 2, 3, 4, 5, and 6. Here is a summary of the different spatial arrangement, the bond angles, and then here we have the names. So definitely keep this on hand whenever you're practicing determining electron geometries. We are going to practice this together. So here we have SiH4 and then we have water, H2O. So previously in the Lewis structure video, we actually drew out the structure already, so I'm not gonna spend time calculating the electrons and everything. I'm just gonna draw it out. So that's where I'm getting that structure from. We verified that this was the Lewis structure for that. And then we are going to determine the electron geometry around that central atom. So here in the silicon has a total of 1, 2, 3, and 4 electron groups around it, right? We're not counting, we don't care if they're bonds, we don't care if they're lone pairs, we're just looking at how many groups are around it. There's a total of 4. Whenever you have 4, you have a tetrahedral electron geometry. Okay, so we're done with this compound. Now let's do H2O. So we're going to have to draw the Lewis structure for H2O. So first you total up the valence electrons. So 2 hydrogens, that's 2 times 1 valence electron. And then we have an oxygen. 1 oxygen is 6 valence electrons. So we have a total of 8 valence electrons we're going to use up. Oxygen is our central atom because there's only one of them. And then we have 2 hydrogens. We start off with single bonds. We used up 4 electrons so far, so we have 4 valence electrons left. I'm going pretty fast here because hopefully you've already gone through the guidelines and you're kind of familiar with them. So I drew single bonds first. I used up 4 electrons. The rest of the electrons will be placed on outer atoms. In this case, these outer atoms are happy already. They have their duet, the hydrogens. So we're going to place them on the central atom. And now the central atom has an octet, and now everything's done. We used up all our electrons and we're done with the Lewis structure. So let's determine how many groups we have around this central atom. We have 1 group, 2 groups, 3, and 4. We have 4 electron groups around it. So actually again, we have our tetrahedral electron geometry for water. So this is a good example, or I like this example, contrasting these examples because we have 2 lone pairs in this case and 2 bonding pairs right here, but total it's still 4. And over here we have just 4 bonding groups. So you can see how the electron geometry can stay the same even if you have different like combinations. And then this is another way I can ask these questions about electron geometry. What is the electron geometry of a central atom with 6 bonding groups? So that would be octahedral. So keep in mind, for some of these problems, you might have to draw out the Lewis structure first, the same way that we did here. I can also just make it kind of easy and just test whether you know the names and the number of bonding groups that are related to each name of the electron geometries.